In the desperate spring of 1941, as war clouds gathered over the Atlantic and Pacific, the United States Navy faced an engineering crisis that would require swift and innovative thinking. The military needed a building that could be transported anywhere in the world, assembled by untrained personnel, and withstand everything from Arctic blizzards to tropical typhoons, from North African sandstorms to the explosive violence of modern warfare. The solution they received would become one of the most iconic structures of the 20th century, the Quonset hut. This simple, half-cylindrical shelter, named after Quonset Point in Rhode Island where it was first deployed, represents a remarkable convergence of engineering principles, material science, and practical ingenuity. Over the course of World War II, approximately 170,000 of these structures were manufactured and deployed across every conceivable climate and combat zone. They served as barracks, hospitals, command centers, warehouses, laboratories, churches, and countless other functions. More remarkably, many still stand today, a testament to the fundamental soundness of their design. The story of the Quonset hut is not merely one of wartime expedients. It is a tale of how engineers, working under extreme time pressure and material constraints, developed solutions to structural problems that would influence architecture and construction for decades to come. Understanding how these structures were designed to survive the most extreme conditions reveals principles of engineering that remain relevant in our modern age of sustainable building and disaster-resistant construction. The Genesis, learning from the Nissen hut. To understand the engineering brilliance of the Quonset hut, we must first look backward to the muddy trenches of World War I. There, a Canadian-American mining engineer named Peter Norman Nissen, serving as a major in the Royal Engineers, recognized a critical problem facing Allied forces. Traditional tented accommodations were inadequate for the Western Front's brutal conditions. Soldiers needed portable, durable shelter that could be rapidly deployed and easily moved as battle lines shifted across the scarred landscape of France and Belgium. Nissen's solution, developed in April 1916, was revolutionary in its simplicity. Drawing inspiration from the curved roof of a drill shed at Queen's University in Kingston, Ontario, he created a semi-cylindrical structure made from sheets of corrugated steel bent over a skeleton of steel ribs. The design could be packed into a standard army wagon and erected by 6 men in just 4 hours. The world record for assembly would eventually stand at a remarkable 1 hour and 27 minutes. The Nissen hut's engineering was elegant. The structure consisted of T-shaped steel ribs positioned at 6-foot intervals with wooden purlins attached to support the corrugated metal skin. The cross-section formed slightly more than a semicircle, with the bottom curving inward to provide additional stability. 3 curved corrugated steel sheets covered the arc of each bay, overlapping by 6 inches at the ends and 2 corrugations at the sides. The entire structure sat on wooden bearers placed on level ground, with the steel ribs bolted directly to these foundations. This design embodied several key engineering principles that would later be refined in the Quonset hut. First, the curved shape provided inherent structural strength through the arch principle, distributing loads efficiently along the curve rather than concentrating stress at right angles. Second, the corrugated steel offered far more rigidity than flat sheets while using the same amount of material, a critical advantage given wartime shortages. Third, the prefabricated design meant that components could be mass-produced in factories and assembled in the field without specialized construction skills. More than 100,000 Nissen huts were produced during World War I, serving not just as barracks, but also as mess halls, kitchens, hospitals, and even churches. However, the design had significant shortcomings that would become apparent in the 2 decades between the World Wars. The biggest complaint concerned thermal performance. The Nissen hut's insulation system relied entirely on the air cavity between interior and exterior corrugated metal panels. This proved woefully inadequate. The huts were bitterly cold in winter and unbearably hot in summer. Additionally, the metal components were susceptible to rust, particularly in humid climates. The complicated paneling system, with corrugated metal on both the interior and exterior, made assembly more time-consuming than necessary. The original design also lacked proper consideration for different climate zones, a fact that would become critical as World War II spread across every continent and climate zone on Earth.
The American innovation, birth of the Quonset. When the United States Navy approached the George A. Fuller Company in 1941, they had specific and demanding requirements. The structure needed to be lightweight enough for easy transport, simple enough for untrained personnel to assemble, economical in its use of scarce materials, and above all, adaptable to serve multiple purposes across vastly different environments. The Navy also stipulated two non-negotiable design features. The structure must be arch-shaped for strength and deflection of shell fragments, and it must have an open interior to allow flexibility of use. Otto Brandenburger, the only licensed architect in the Fuller Company design team, took on the challenge. Brandenburger brought a unique combination of qualifications to the project. His experience reviewing plans for the Works Progress Administration had taught him the importance of economical design and efficient use of materials. His service in the United States Army gave him first-hand understanding of soldiers' needs in the field. These credentials made him ideally suited to understand both the technical requirements and the practical realities of military construction. Brandenburger assembled a team that included Robert McDonald, Tommasino Secundino, and Dominic Ergo. Together, they analyzed the Nissen hut design, identifying its strengths and weaknesses. The team recognized that while the basic arch concept was sound, significant improvements were needed, particularly in insulation, assembly efficiency, and material usage. Their breakthrough came in addressing the thermal performance problem that had plagued the Nissen design. Rather than relying on an air gap between double layers of corrugated metal, the Quonset hut would use a three-layer wall system. The exterior would be corrugated metal panels mounted on wooden purlins, providing weather protection and structural rigidity. Inside this outer shell would be a 1-inch thick layer of paper insulation. Finally, a thin, lightweight, pressed wood lining of 3/16-inch masonite would cover the interior, held to the rib flanges with specially designed attachment clips. This seemingly simple change represented sophisticated engineering thinking. The paper insulation provided a thermal barrier far more effective than an air gap. The masonite interior lining created a finished surface that was smooth, easy to clean, and suitable for various military uses. Most importantly, this wall system was lighter and less expensive than the Nissen double corrugation approach while providing superior performance. The original T-ribbed Quonset hut followed the Nissen dimensions quite closely, with a 16-foot diameter and identical steel arched frames. However, the American engineers made crucial improvements to the structural framework itself. The ribs were made from steel members with a cross-section measuring 2 inches by 2 inches by 1/4 inch in a T-shaped, optimized to provide maximum strength with minimum weight. Working with incredible speed driven by the urgency of approaching war, the Fuller Company moved from contract signing to production of the first unit in just 60 days. By the time the full design was finalized, they had created a structure that could be shipped in 12 crates, weighing a total of 3,212 pounds without contents, and assembled by a 10-person team in a single day using only hand tools.
The science of the arch. Why curves conquer force. The most fundamental engineering principle underlying the Quonset hut's remarkable resilience is the arch itself. To understand why this shape proved so effective against storms, explosions, and extreme loads, we must delve into the physics of structural mechanics. When weight is placed on top of a flat roof or wall, it creates what engineers call compression forces that travel straight downward through the structural members to the foundation. This vertical load must be resisted by the strength of the materials themselves. In a right-angled structure, the junction points where walls meet roofs are particularly vulnerable. They become stress concentration points where forces can cause failure. An arch operates on an entirely different principle. When load is applied to the crown of an arch, the force is redirected outward and downward along the curve. This transforms vertical compression into a combination of compression and lateral thrust. Because the arch is curved, Every point along its length helps support the load, distributing stress more evenly throughout the structure. The force ultimately transfers to the supports at the arch's base, known as abutments, where it is anchored into the foundation. This load distribution makes arches inherently stronger than flat or angled structures of equivalent material thickness. An arch can support far more weight than a horizontal beam made from the same amount of material. This principle has been understood since ancient times. Roman architects used it to build aqueducts that still stand 2 millennia later, but the Quonset hut applied it in a modern, industrialized context. The semi-cylindrical shape of the Quonset hut essentially creates an arch in 3 dimensions. Rather than supporting load at just 2 points like a traditional arch, the cylindrical form distributes forces continuously along its entire length. This makes the structure exceptionally resistant to loads applied from any direction, not just vertical weight from above, but also lateral forces from wind and even ground movement from earthquakes. The corrugation of the steel skin adds another layer of engineering sophistication. Flat metal sheets are relatively weak. They bend easily under load. Corrugation creates a series of ridges and valleys that dramatically increase the sheet's ability to resist bending forces. Think of it this way. A flat piece of paper is flimsy, but fold that same paper into a series of accordion pleats and it becomes remarkably stiff. The corrugated steel in a Quonset hut gains similar strength multiplication. Studies have shown that corrugated metal buildings are approximately 5 times stronger than comparable structures built with non-corrugated panels. This corrugation serves a dual purpose in the Quonset design. Not only does it strengthen the metal skin, but the ridges also help water shed efficiently from the curved surface. Rain, snow, and debris naturally slide off the arch shape rather than accumulating and adding to the structural load. The overlapping installation of the corrugated panels, with each sheet lapping over the next by 2 corrugations on the sides and 6 inches at the ends, creates a shingled effect that further enhances water shedding while preventing infiltration. The combination of arch geometry and corrugated construction creates what engineers call a shell structure. Like an eggshell, which achieves remarkable strength through its curved form despite being very thin, the Quonset hut derives its structural integrity from its shape as much as from the properties of its materials. This efficient use of materials was crucial during wartime, when every pound of steel had to be justified. Designing for the storm. Wind resistance through aerodynamics. One of the most challenging engineering problems the Quonset hut designers had to solve was creating a structure that could withstand the violent winds common in many deployment locations. From the howling gales of the Aleutian Islands, to the typhoons of the Pacific Theater, to the hurricanes of the Caribbean, military installations faced some of the most extreme wind conditions on Earth. Traditional rectangular buildings present several vulnerabilities to high winds. The flat surfaces of walls and roofs create large areas where wind pressure can apply force directly. Right-angled corners create turbulence and vortices that can generate powerful suction forces. Most critically, wind flowing over a flat roof creates a pressure differential. Higher pressure below the roof and lower pressure above that can literally lift the roof off the building in extreme conditions. The Quonset hut's curved profile addresses all of these vulnerabilities through principles of aerodynamics. When wind encounters the curved surface of the hut, it flows smoothly over the arc rather than striking a flat surface. This smooth flow dramatically reduces wind pressure on the structure compared to what a flat wall would experience. The absence of a horizontal roof surface eliminates the primary failure point in conventional buildings. There is no discrete roof to be lifted off because the walls and roof are a continuous curved surface. The semicircular shape also eliminates overhangs and eaves, which are particularly vulnerable to wind damage. Traditional roof overhangs can act like airplane wings in high winds, generating lift forces that tear them away from the structure. The Quonset hut's lack of projecting elements gives the wind no purchase to catch and tear. Engineers working on the Quonset design understood that wind doesn't just push, it also creates complex pressure patterns around structures. On the windward side, positive pressure pushes against the building. On the leeward side and around corners, negative pressure, or suction, pulls at the structure. The curved surface of the Quonset hut minimizes these pressure differentials. Wind flowing over the smooth arc creates a more uniform pressure distribution, reducing peak stresses. This aerodynamic efficiency was dramatically demonstrated during Super Typhoon Karen in 1962, which struck Guam with devastating force. While conventional buildings were destroyed en masse, photographs from the aftermath show large numbers of Quonset huts still standing, their curved forms having successfully deflected the typhoon's fury. Similar performance has been documented in countless hurricanes, with properly anchored Quonset structures surviving storms that leveled surrounding conventional buildings. Modern testing has validated these wartime observations. Engineers have subjected Quonset-style buildings to wind tunnel testing and projectile impact trials. In one memorable test, a wooden plank was hurled at 100 miles per hour into a Quonset panel. It barely dented the steel. Contemporary Quonset huts built to current standards have achieved HVHZ, High Velocity Hurricane Zone certification, meaning they can withstand winds of 100 miles per hour or more, along with the impact of debris propelled at hurricane speeds. The wind resistance of the Quonset hut also depends crucially on proper anchoring. The arch transfers wind loads down to the foundation through compression and outward thrust. If the base of the arch is securely fastened to a solid foundation, the entire structure acts as a unit, resisting uplift and lateral movement. The original military Quonset huts were bolted to wooden bearers, which were in turn anchored to the ground or to concrete piers. This connection was critical. A structure is only as strong as its weakest link, and the foundation connection is where many buildings fail in high winds. Engineers also had to consider the cumulative effect of wind on large installations. Multiple Quonset huts placed in close proximity could create wind channeling effects, where wind accelerating between buildings generates higher velocities than the ambient wind speed. Military bases were planned with spacing and orientation that minimized these effects, though the robust individual strength of each hut provided a safety margin against unforeseen aerodynamic interactions.
Tropical challenges, engineering for heat and humidity. Perhaps no environment tested the Quonset hut design more severely than the tropical Pacific theater. Islands like Guam, Guadalcanal, and countless coral atolls presented a punishing combination of challenges: intense solar radiation, high humidity, salt spray, tropical storms, and dense vegetation hosting insects and fungi. The engineers who adapted the Quonset hut for these conditions had to solve problems that would have significant implications for post-war tropical architecture. The fundamental thermal challenge of a metal building in the tropics is straightforward. Metal is an excellent conductor of heat. Under the tropical sun, the exterior steel skin of a Quonset hut could reach temperatures exceeding 150 degrees Fahrenheit. Without proper thermal barriers, this heat would rapidly conduct through to the interior, creating an oven-like environment unsuitable for human habitation or storage of temperature-sensitive materials. The insulation system developed for the original T-ribbed Quonset, 1 inch of paper insulation between the corrugated steel exterior and masonite interior lining, provided a basic thermal barrier. However, this proved insufficient in the most extreme tropical conditions. The paper insulation could absorb moisture in high humidity, reducing its effectiveness and potentially leading to mold growth. The thin masonite interior, while providing a finished surface, did little to contribute to thermal resistance. Military engineers deployed to the Pacific made numerous field modifications to address these shortcomings.
One of the most effective was simply elevating the huts on concrete blocks or pilings. This created an airspace beneath the floor that served multiple purposes. The air circulation under the raised floor helped dissipate heat, preventing the ground from acting as a heat sink that would warm the interior from below. The elevation also protected against flooding during tropical downpours and reduced termite access to wooden components. Ventilation became a critical concern. The original Quonset design included doors and windows in the plywood end walls, but the semicircular side walls had no openings. In tropical heat, interior air could become stagnant and oppressively hot. Field engineers added ventilation in various ways. Some installations cut additional openings in the end walls to create cross-ventilation. Others installed ridge vents along the peak of the arch, allowing hot air to escape from the highest point where it naturally accumulated. The Navy formally recognized the need for climate-specific designs and developed specialized variants. The tropical design Quonset incorporated improved ventilation systems, including strategically placed louvers and vents. Some versions used lighter-colored exterior finishes to reflect rather than absorb solar radiation. Experiments with different insulation materials sought substances more resistant to moisture and tropical deterioration. The problem of corrosion in tropical environments proved equally challenging. Salt-laden air combined with high humidity created ideal conditions for rust. The original Quonset huts used low-grade steel, which quickly showed signs of oxidation in coastal tropical locations. Within months, red rust could appear, weakening the metal and creating maintenance headaches. The Navy responded by switching to higher-grade, rust-resistant steel alloys for tropical deployments. Even rust-resistant steel required protective coatings. Military engineers developed specialized paint systems for tropical Quonset huts. These weren't merely decorative, they were engineered coatings designed to seal the steel from moisture and salt. The application process was critical. Any area of exposed or improperly coated steel would become a corrosion initiation point. After the war, the prevalence of Quonset huts led to Sherwin-Williams to develop Quoncoat, a paint specifically formulated for adhesion to corrugated metal and resistance to harsh environments. The Pacific Hut represented an alternative engineering solution to tropical challenges. Designed by Seattle-based mechanical engineer Frank Hobbs, this variant replaced the all-steel construction with an all-wood design. The frame was constructed from wood rather than steel ribs, and the exterior was covered in Celotex, a waterproof form of masonite, rather than corrugated metal. This design addressed the thermal transfer problem directly, as wood is a far poorer conductor of heat than steel. The Pacific Hut also featured a distinctive triangular ridge vent cover for improved air circulation. The U.S. Army ordered 1,000 of these units, recognizing that in some tropical applications, the reduced thermal transfer of wood construction overweighed the structural advantages of steel. Another tropical adaptation, the MK Hut, designed by the Morrison-Knudsen Company, took a similar wood-based approach. Company legend attributed the design inspiration to a chicken shed, though the engineering was considerably more sophisticated. These wooden variants demonstrated the flexibility of the basic arch principle. The structural advantages of the curved form could be realized with different materials optimized for different environmental challenges. The long-term performance of Quonset huts in tropical environments revealed both successes and limitations. In Guam, where thousands of Quonset huts were deployed during and after the war, the average lifespan was about 50 years, remarkable for structures originally designed as temporary facilities. The curved shape that helped them survive typhoons made them difficult to expand or modify, as the lack of vertical walls made additions challenging. The heat accumulation inside remained a persistent complaint, even with modifications. Corrosion from heavy tropical rains and salt air gradually weakened the steel, particularly in areas where protective coatings had been damaged. Yet many Quonset huts continued to serve in tropical locations decades after their construction. Their survival speaks to fundamental soundness of the design and the quality of engineering that went into their development. The lessons learned from tropical Quonset deployments influenced post-war architecture throughout the Pacific region, informing approaches to ventilation, corrosion resistance, and thermal management that remain relevant in tropical construction today.
Surviving explosives, the bomb-resistant design.
One of the most remarkable and often overlooked engineering features of the Quonset hut was its ability to survive explosive blast effects. This characteristic, while not always part of the initial design criteria, proved crucial during wartime deployment. Understanding how the Quonset structure responded to explosions reveals sophisticated interaction between material properties, structural geometry, and the physics of blast waves. When an explosion occurs, it generates a blast wave, a sharp, intense pulse of pressure that radiates outward from the detonation point. This pressure wave travels at supersonic speeds, striking structures with tremendous force. The blast wave isn't uniform. It consists of two phases. First comes the positive pressure phase, a sharp spike of intense overpressure that pushes outward. This is followed by a negative pressure phase, where pressure drops below ambient, creating suction. Both phases can damage structures, but through different mechanisms. Traditional rectangular buildings present several vulnerabilities to blast waves. Flat walls catch the blast wave like a sail catches wind, transmitting shock loads through rigid structural members to connection points. These connections, where walls meet roofs, where posts connect beams, become stress concentration points where catastrophic failure can initiate. The rigid, angular geometry creates reflection patterns that can amplify pressure locally. Windows and doors, being the weakest points in walls, often fail first, allowing the blast wave to enter the building's interior where it can cause devastating secondary damage. The Quonset hut's curved steel construction responds to blast effects in a fundamentally different way. The smooth, curved surface deflects blast waves rather than catching them. The semicircular profile presents no flat surfaces perpendicular to the blast direction. Instead, waves flow over and around the structure. This deflection dramatically reduces the pressure applied to the building compared to what a flat wall would experience from the same blast. The flexibility of the steel shell provides another layer of protection. Unlike rigid structures that resist deformation until they catastrophically fail, the Quonset hut's corrugated steel can flex and deform elastically, absorbing energy from the blast wave. This flexibility allows the structure to breathe in response to the pressure pulse, much like a shock absorber in a vehicle. When the blast wave passes, the steel springs back to its original shape, assuming the deformation hasn't exceeded the material's elastic limit. One of the most valued characteristics noted during the war was the Quonset hut's ability to contain and lift during internal explosions. This might seem counterintuitive. Why would you want a building to lift? The answer lies in pressure relief. If an explosion occurs inside a rigid structure, the blast pressure rapidly builds until it finds the weakest escape route, usually by blowing out walls or roof. The Quonset hut's relatively flexible structure and its attachment to the foundation allows it to lift slightly at the base during an internal explosion, venting pressure before it builds to destructive levels. This pressure relief prevents the catastrophic rupture that would occur in a more rigid structure. This characteristic made Quonset huts particularly suitable for storage of ammunition and explosives. If an accidental detonation occurred, the structure could contain some of the blast effects while venting pressure in a way that minimized damage to surrounding structures. Many military installations used Quonset huts as ordnance storage specifically because of this behavior. A specialized variant, the Armco hut, was built with heavier steel specifically for ordnance storage and to serve as air raid shelters. The arch structure also provides protection against blast-induced ground shock. When explosives detonate on or in the ground, they create seismic waves that propagate through the earth, causing secondary damage to building foundations. The Quonset hut's continuous arch transfers these ground-transmitted forces more evenly throughout the structure, reducing localized stress concentrations that could lead to failure. The all-steel construction of the Quonset hut provides inherent fire resistance that complements its blast resistance. Unlike wooden structures, which can be ignited by the thermal pulse of an explosion or by secondary fires, steel doesn't burn. While extreme heat can weaken steel structural properties, the Quonset hut's material won't add fuel to fires, a critical advantage in combat zones and ammunition storage areas. This earned Quonset and other all-steel arch structures an A fire rating. Engineers documented the blast performance of Quonset huts, both from combat experience and deliberate testing. Structures subjected to near-miss bomb strikes often remained standing, albeit with deformation, when nearby conventional buildings were leveled. Post-war analysis of damage patterns helped refine understanding of how curved steel structures respond to explosive loads, informing the development of hardened structures for military and industrial applications. The debris resistance of the Quonset hut, while primarily understood in the context of storm protection, also proved valuable against blast-driven projectiles. Explosions turn everything nearby into high-velocity shrapnel. The curved, corrugated steel of the Quonset hut provides better protection against such projectiles than the flat wooden walls typical of temporary military structures. The corrugations themselves help deflect impacting debris rather than presenting a flat surface that receives the full force of impact. However, the Quonset hut wasn't invincible. Direct hits from bombs or large-caliber artillery would, of course, destroy the structure. The thin steel skin couldn't withstand penetration by armor-piercing projectiles or shape charges. The design's blast resistance was most relevant for near-miss scenarios, accidental internal detonations, or exposure to blast waves from distant explosions. Modern analysis has validated and expanded understanding of how art structures respond to explosions. Finite element analysis allows engineers to simulate blast loading on curved steel structures, optimizing designs for specific threat scenarios. Contemporary protective structures for sensitive facilities often incorporate the arch principle, though typically with much thicker steel and often buried or baffled for enhanced protection. The Quonset hut's performance demonstrated that even relatively thin steel, properly formed and deployed, could provide meaningful blast protection.
Arctic adaptation, engineering for extreme cold. While tropical heat and typhoons presented one extreme of environmental challenge, the opposite end of the climate spectrum posed equally severe engineering problems. Quonset huts deployed to Arctic and subarctic regions, from Alaska to Iceland to the remote islands of the Aleutian chain, had to contend with temperatures plunging to -40 degrees, howling winds, heavy snow loads, and the unique challenges of permafrost and ice. The fundamental thermal problem in cold climates is the reverse of tropical conditions: how to retain heat inside the structure rather than allowing it to escape. Metal's excellent thermal conductivity, an advantage for heat dissipation in warm climates, becomes a severe liability in the cold. Steel structural members can create thermal bridges that conduct heat rapidly from the warm interior to the frigid exterior. In extreme cold, metal components can become brittle, changing their structural properties in ways that increase failure risk. The standard Quonset hut insulation system, 1 inch of paper insulation, proved woefully inadequate for Arctic conditions. Engineers quickly recognized that Arctic deployments required substantially enhanced thermal barriers. Field modifications often doubled or tripled insulation thickness, packing additional layers between the structural ribs. Glass fiber insulation, superior to paper in moisture resistance and thermal performance, was used where available. The James Way hut represented a specialized design solution for Arctic conditions. Manufactured by James Manufacturing Company of Fort Atkinson, Wisconsin, this variant used wooden ribs instead of steel, eliminating the thermal bridging problem. The wooden frame was covered with insulated blankets consisting of glass fiber insulation faced with flame-proof muslin and enclosed in plastic-treated cotton that was water, vermin, and fireproof. These blankets came in 4-foot-wide sections that could be assembled even by personnel wearing bulky cold-weather gear and mittens. The James Way design embodied several clever engineering solutions. The insulated fabric covering provided excellent thermal resistance while being lightweight. A complete 16 by 16-foot hut weighed just 1,200 pounds. The wooden packing crates were designed for reuse as the hut's floor, eliminating waste and reducing the material that needed to be transported. The fabric construction allowed the hut to be assembled extremely quickly, critical when construction crews were working in brutal cold. The trade-off was reduced durability compared to steel construction. Fabric huts required more maintenance and had shorter service lives, but in extreme cold, getting shelter erected quickly often took precedence over longevity. Snow loading presented another major engineering challenge. In Arctic regions, snow accumulation on roofs can reach several feet. This represents an enormous weight. Wet snow can weigh 15 to 20 pounds per cubic foot, meaning that just 2 feet of snow on a 20 by 48-foot Quonset roof could add more than 14,000 pounds of load. The structure must be able to support this weight without collapse, while also being steeply enough curved that snow will slide off rather than accumulating indefinitely. The Quonset hut's semicircular profile provides an excellent angle for snow shedding. Snow tends to slide off surfaces pitched steeper than about 30 degrees from horizontal. The Quonset's continuously curving surface exceeds this angle over most of its upper area. However, engineers learned that snow could still accumulate in certain patterns, particularly drifts that formed on the leeward side of the structure. Proper site selection and orientation relative to prevailing winds helped minimize problematic drifting. The corrugated steel surface also aided snow management. The ridges of the corrugation created a slightly rough surface that helped break up snow layers, promoting sliding. Some installations applied low-friction coatings to the steel to further reduce snow accumulation. In areas of extreme snow load, engineers specified heavier gauge steel or added additional structural reinforcement to increase load-bearing capacity. Foundation design for Arctic Quonset huts required special consideration of permafrost, permanently frozen ground that underlies much of the Arctic. Permafrost presents unique challenges for construction. If a heated building is placed directly on permafrost, the heat from the building can thaw the frozen ground beneath it. As permafrost thaws, it often contains large amounts of ice. When this ice melts, the ground subsides, potentially causing severe structural damage. This differential settlement can crack foundations and twist structures. Engineers addressed permafrost by designing elevated foundations that created an airspace between the ground and the building floor. This airspace, ventilated to maintain cold temperatures, preserved the permafrost beneath the structure. Quonset huts in Arctic locations were often placed on timber pilings driven into the permafrost or on gravel pads that provided both drainage and thermal insulation. The elevated design had the additional benefit of preventing snowdrifts from burying entrances. Alaska's remote military installations pioneered an ingenious transportation method for Arctic Quonsets. Rather than disassembling structures for relocation, engineers mounted entire huts on sled runners. These could then be dragged across frozen terrain by tractors, allowing rapid repositioning of facilities as military needs changed. This method was only practical because of the Quonset's relatively light weight and unitary construction. Trying to move a conventional building this way would have been impossible. The issue of ice formation required careful engineering attention. Ice could form on the exterior of the structure, adding weight and potentially damaging the corrugated steel skin as it expanded. Interior moisture was equally problematic. In cold climates, warm moist air from cooking, breathing, and other activities can reach the cold exterior surface, where it condenses and freezes. This ice formation inside the walls can damage insulation and structural components. Proper ventilation became critical. Arctic Quonsets needed enough air exchange to remove moisture-laden air while not losing excessive heat. Cold weather materials selection extended beyond insulation to every component. Fasteners, seals, and gaskets had to be made from materials that remained flexible at extreme temperatures. Standard rubber seals become brittle and crack when cold. Arctic installations used synthetic materials engineered for low-temperature performance. Lubricants for doors and mechanical systems had to be formulated for cold weather. Even the paint systems required special consideration. Some paints crack or peel at very low temperatures. The combination of cold temperatures and wind created wind chill effects that increased heat loss. The Quonset's aerodynamic shape, advantageous for wind resistance, also minimized wind chill by promoting smooth airflow over the structure rather than allowing turbulent eddies to increase surface heat transfer. This subtle benefit of the curved design helped reduce heating requirements. Heating systems for Arctic Quonsets had to be carefully engineered. The relatively small interior volume meant that heat sources could maintain comfortable temperatures even in extreme cold, provided the structure was properly insulated. However, heating also had to be managed to prevent creating hot spots that might damage materials or create fire hazards. Many Arctic installations used forced air heating systems that distributed warmth evenly, rather than relying on radiant heaters that could overheat local areas. The successful deployment of tens of thousands of Quonset huts across Arctic and subarctic regions demonstrated that the basic design could be adapted to the most extreme cold weather conditions. The modifications required enhanced insulation, foundation design for permafrost, material selection for low temperatures represented engineering responses to specific environmental challenges, while retaining the fundamental advantages of the arch structure: strength, rapid assembly, and efficient use of materials.